Okay, so now let's solve some problems. Practice problem 2B part, question number 3, part A. 40-Newton child and 30-Newton child sits on either end of 2-meter long seesaw. So we will draw a 2-meter long seesaw first. So this is a seesaw. So length is 2 meters. 2 meters. And one child is 400 newtons, sits in one end. So then let's locate one on one end. So I will locate 400 Newton child on the left hand. Other child is on the right hand. 300 Newton child is on the right hand. Where along the seesaw should the pivot be placed to ensure the rotational equilibrium? So we are going to balance this seesaw by locating a support, which is pivot means support. So we will locate the support. Remember, to balance such a system, you should locate the support closer to heavier one. Of course, 40 Newton is the heavier. You are going to locate it, the support closer to 40 Newton. But how close? And how many meters this distance or that distance? We should calculate this by using rotational equilibrium. So when we locate a support here, support, of course, will apply an upward force. So there are two downward forces towards the center of the earth, 400 Newton and 300 Newton. Of course, this support must apply an upward force, which is known as normal force, which must be equal to Fn. According to the translational equilibrium, sum of the force acting on the beam must be equal to 0. 400 plus 300, which is 700 downward. So then Fn must be also 700, which is upward force. But the question is not about the normal force. It's about what is that distance. So where along the seesaw should the pivot be placed means you are going to find the location of this support or pivot. So there are two methods for solving this problem. One of them is you are going to choose this point as axis of rotation. So one side of the support you are going to say x, unknown. So other side is going to be total distance is 2. That distance is x. It's going to be 2 minus x. In this case, rotational equilibrium, you are going to write the rotational equilibrium of this seesaw with respect according to this pivot point, which is O, axis of rotation. So then these two forces produces torque. So 300 Newton force produces a torque. If you push it in the direction of 300 Newton, so it's going to be clockwise. It's a negative torque. But 400 Newton force, which is the weight of the heavier child, will produce a counterclockwise torque. How? You fix it from the axis of rotation, push in the direction of the force, so it's going to be rotating in counterclockwise direction, so positive. And because Fn is acting on the axis of rotation, so it produces zero torque. So then let's calculate torque of 300 Newton. So which is equal to 300 multiplied by distance from force to axis of rotation. We said it's 2 minus x. So then which is equal to 300 times 2, which is 600, minus 300 times x, 300 x. This is torque produced by 300 Newton force. And let's calculate the torque produced by 400 Newton force. It's equal to 400 multiplied by distance from force to axis of rotation, which is x, which is positive. Yeah. So then we calculate the torque of each force, then apply the condition for rotational equilibrium, because it is in rotational equilibrium question says net torque must be equal to 0, which means 400x plus torque of 300, which is plus 600 minus 300x plus torque of Fm, which is 0, must be equal to 0. So 400x and 400x minus 300x plus 600 is equal to 0. So let's check it. I think we forgot to put negative here. Here is the negative because this torque is negative. Negative times negative 600, 300 times 2, negative 600. Negative times thing is positive. So we should put it here negative. Here is positive. Then it's going to be positive and negative. So 400x plus 300x, which is equal to 700x. This negative on the other side positive, which is equal to 600. Then x is equal to 600 divided by 700. Let's calculate it. What is x equal by calculator? 600 divided by 700, which is equal to 0.786. 0.86 meter is x. What is x here? X is the distance from the pivot to 400 Newton child. So this distance is calculated as 0.86 meter. Then what about other distance? So other distance, other side, is going to be 2 minus x. 2 minus 0.86, which is equal to, so let's calculate 2 minus 0.86, 1.14. So this side must be 1.14 meters. So then we can say that, yes, pivot point or fulcrum must be located at 1.14 meter from 300 Newton child or 0.86 meter from 400 Newton child. So this is the answer of this question. And same question, part B. Suppose as 225 Newton child sits 0.2 meter from 400 Newton child, where must a 325 Newton child sit to maintain rotational equilibrium? So after we provide the rotational equilibrium by these two children, and we found that there are two child. One of them is 300 Newton child. Remember, it was the part A, and other one is 400 Newton child, and the fulcrum must be located 0.86 from 400 Newton child and 1.14 from 300 Newton child. We calculated like this in part A, and we provided rotational equilibrium. But later, two more children sit on either side of the fulcrum. One child is 225 Newton and sits 0.2 meter from the 400 Newton child. So that distance is given 0.2 meters. If this distance is 0.2 meter, which means this 225 Newton child is at a distance of 0.86 minus 0.2 from the fulcrum, because that total distance is 0.86. This small distance is 0.2. That distance must be 0.86 minus 0.2, which is equal to 0.66, which means 225 Newton child is sitting at a distance of 0.66 meter from the fulcrum. So where must other child, which is 325 Newton, sit to maintain again rotational equilibrium? So then we will find what is that distance. I will say x. We will find this. Because these two children are balanced, so we don't need to add them into the rotational equilibrium part. Again, we are going to think that there are two children. One of them is 225, the other one is 325, and one of them is at the distance of 0.26. What is the distance of the other one from the fulcrum? We are going to apply again the rotational equilibrium. So this 225 Newton rotates the try to rotate the fulcrum in clockwise direction, so its torque is negative. Let's calculate negative 225 multiplied by distance from first axis of rotation 0.66. So let's calculate this. 225 multiplied by 0.66, which is equal to 1148.5. negative 148.5 Newton dot meter. And other 300 Newton, 325 Newton child try to rotate the beam in the counterclockwise direction. So that's why it's positive. Positive 325 is the force, distance from force to the extra rotation is x. So this is the one force, torque, the other one is another torque, and then we know that Fn is acting on extra rotation, it's 0. These two children are balanced already. That's why we are going to add these two torque and make them equal to 0 again. Which means 325x minus 148.5 Newton must be equal to 0, which is some net torque must be equal to 0. Then 325x is equal to 148.5, and after that divide 148.5 by 325, which is equal to 0.46, almost 0.46. X is equal to 0.46 meters. So which means this 325 Newton child must sit at to 0.46 meter, and that distance must be 0.46 meter from the fulcrum to maintain the rotational equilibrium again. And another practice problem. A 700 Newton window washer is standing on a uniform scaffold supported by a vertical rope at each end. The scaffold weighs 200 Newton and 3 meter long. So it's a beam. Scaffold is a beam. Draw a beam which is 3 meter long. So then that distance is going to be 3 meter long, and this scaffold weighs 200 Newton, and it's the uniform. When it says, you are going to say that center of gravity is the midpoint. So this 200 Newton of the scaffold, weight of the scaffold must be drawn as a gravitational force from the center of gravity, which is the midpoint. So this is 1.5 meter. That is 1.5 meter. So then gravitational force Fg, which is equal to 200 Newton, is acting from this point. And this scaffold is supported by vertical ropes at each end. So let's support it by two ropes. One rope at one end, acting one end, and another rope is connected to attached to the other end. Of course, each rope must produce a tension force, so it must pull the rope up to the sky, which is F1. I'm going to say it on the right, F2 on the left. So then questions that 700 Newton window washer, he's a man, is standing on the scaffold 1 meter from one end. So it can be from right hand or left hand, it's up to you. So I will choose it from the left hand. So let's locate the man's here, the window washer here. So this window washer must apply a force downward, which is equal to 700 Newton. 700 Newton, and at a distance of 1 meter from one end. I choose the left hand. Okay, so then what is the force in each rope? Calculate F1 and calculate F2. So there are two unknown forces. If there are two unknown forces, you cannot start solving this problem by translational equilibrium. You need to apply the rotational equilibrium first. To find this, you should choose the location of one of the unknown force as axis of rotation, and my method is generally choosing the left end as an axis of rotation. So then torque of F2 will be 0. Other three forces will produce torque, and then direction of the torque for 700 and 200 is because they are trying to rotate clockwise, so then they are negative torque and then negative torque. But F1 is trying to rotate counterclockwise, positive torque. Let's calculate them. 700 Newton force produces a torque. Let's write it. It is negative 700 multiplied by distance from force to axis of rotation. We choose that distance. Its question says it's 1 meter from one end. We choose this is the end. So multiplied by 1, which is equal to negative 700 Newton meter. So this is the torque of 700 Newton force. Now let's calculate torque of 200 Newton force. It is also negative 200 multiplied by distance from force to axis of rotation. That distance is, because it's midpoint, 1.5. We should multiply it by 1.5. Negative 200 multiplied by 1.5, negative 300 Newton dot meter. This is the torque of 200 Newton force. And F1 is the other force, which is positive torque. It produces a positive torque, F1. Distance from force to axis of rotation, it is the length of the scaffold, which is 3 meters, multiplied by 3. This is the third torque. So then we are going to add all these torque, and then we will apply the rotational equilibrium. Net torque acting on the scaffold must be equal to 0, which means 3F1, which is torque of F1. Continue, negative 300, negative 700. And because this has a 0 torque, let me write from 0 is equal to 0. So then 3F1 is equal minus 1000 is equal to 0. F1 is equal to 1000 divided by 3. If we divide it, 333.3 Newton is F1. Now we found one of the force, F1, which is equal to 300 and, let me write it here, F1 is 333.3 Newton. We found it. And if this is found, which means there is only one unknown force is left, which is F2. If there is only one unknown, so you can apply the translational equilibrium. Now first we applied the rotational equilibrium. Now translational equilibrium. What is translational equilibrium? Some of the forces, not torque. We are not dealing anymore about the direction of the rotation or something like that. Just we will look direction of the force. Some of the force acting on the beam or on the scaffold must be equal to 0. Because all the forces are in vertical, I am going to write it according to y components. So I will start from from left side or right side. It's up to you. F2 is acting upward, so it's positive. 700 Newton is acting downward, so it is negative. 200 and acting downward in negative y, it is 200. Negative 200. F1 is acting upward, positive F1. We found it by time. F1 is 333.3. So some of them must be equal to 0. We added all the forces in vertical along the y direction, according to their directions, of course. And then we are going to find what F2 is. F2. So let's add the other addition of the other forces. Negative 700, negative 200, plus 333.3, pardon, 333.3 is equal to negative 566.7, which is equal to 0. Then F2 is going to be 566.7 Newton. So we found each forces. F1 is found by applying rotational equilibrium. F2 is found by applying translational equilibrium, which is equal to 566.7 Newtons. And sample problem. Sample problem is maybe the longest problem. Not hardest, I don't define the problems hardest, but longer than the others. A uniform 5 meter long horizontal beam that weighs 315 Newton. So there is a very long beam, 5 meter long. Weight of this beam is 315, and it is uniform, which means center of gravity is the midpoint. So that's why we are going to draw 315 newtons from the midpoint, which means that distance must be 2.5 meters. So, because center of gravity divide the beam into two. Attached to a wall by a pin, yes, this is the pin attached to a wall. Its far end, other end, is supported by a cable. Yeah, this is a cable. that makes an angle of 53 degrees with the horizontal. So this angle is 53 degrees. It's given as in the question. And 545 Newton person standing 1.5 meter from the pin. There is a person. This person is standing, which means, of course, if this person is standing on the beam, pushing the beam down with gravitational force, weight of the person, it is 545 Newton, and that distance from pin to the person, it is 1.5 meter. Yeah. Find the force in the cable. This cable, of course, applies a force, tension in the cable. I am going to say it is Ft. And the force exerted on the beam by the ball R. So here, the force acts on the beam by this pin or wall. What is this force? How much? If the beam is in equilibrium, that is the keyword. So we are going to apply, of course, rotational equilibrium and also translational equilibrium to find these two forces. There are two unknowns. One of them, then this cannot be used alone. So we will start with translational equilibrium. For that, as in first, we should determine the axis of rotation. There are, in fact, three unknowns. Ft, R, and R is making an angle. That's why we cannot choose Ft as axis of rotation. If we choose Ft as axis of rotation, R and theta is unknown. There will be two unknowns. But if I choose this point as axis of rotation, R becomes out of the equation, but Ft, I know what is the angle of Ft. That's why you should start solving this problem by choosing the location of the R, which is the pin, is the axis of rotation. And then, according to this point, you are going to define the torque of each forces. You are going to calculate them. After that, you will add them and then make them equal to 0 to find what Ft is. Okay, let's find them. So I fixed from the axis of rotation, which is O. So 445 Newton makes a rotation which is clockwise, but Ft, let's push in the direction of Ft, it is counterclockwise. So this produces counterclockwise rotation, positive torque. This produces clockwise rotation, negative torque. Again, clockwise rotation, negative torque. This is 0. Now let's calculate torque. Each torque equals negative 545, torque is negative, multiplied by distance from force to axis of rotation is 1.5. Let's multiply it. Negative 545 multiplied by 1.5, which is equal to negative 817.5 Newton dot meter. So this is the torque of 545 Newton. And then let's find the torque of 315 negative. It's negative 315 multiplied by distance from force to axis of rotation 2.5 meter multiplied by 2.5. So 315 multiplied by 2.5, which is equal to negative 787.5 Newton dot meter. So this is the torque of second force, and one more force is Ft. Ft produces a positive torque, force is Ft, yes. Distance from force to axis of rotation is 5 meter multiplied by 5, but there's also angle. So sine of this angle is 53. So 5 multiplied by sine of 53, which is equal to almost 4. That's why this torque is equal to 4 times Ft. Torque of R is 0 because it's acting on axis of rotation. Now we calculated the torque of each forces. Now add them and make them equal to 0 and find the unknown force. So sum of the torque acting on the beam must be equal to 0 because there is the equilibrium. And then add them all. Let's start. 4Ft negative 787.5 Negative 817.5 plus 0 is equal to 0. So now let's add them. Negative 787.5, negative 817.5, which is equal to negative 1575. For ft, negative 1575 is equal to 0. ft is equal to divided by 5, which is equal to 300, pardon, not divided by 5. So 4ft is equal to 1575. So we take it other side as positive. 1575 divided by 4 is equal to almost 394 Newton is the tension force in the core. We found one of the force. And now we will find other one, R. But R cannot be used by rotational equilibrium. Translational equilibrium, we are going to apply translational equilibrium. How? Sum of the force acting on the beam must be equal to 0. This is the translational equilibrium. But here a force has two components. That's why you should continue with the components. Sum of the force on X must be equal to 0. Sum of the forces on Y must be equal to 0. Let's start with X. We don't know Rx, that's why unknown must be written as X. Second force has no X component because it's on Y. Third force has also no X component because it's on Y. But fourth force has an X component in which direction? In negative X direction. So how can I calculate this component Ftx? Ftx is equal to F times cosinus 53. So let's add it. It is in negative X direction, that's why we are going to look at it negative. F times cosinus 53. F is, we calculated as 394 multiplied by cosine 53 must be equal to 0. Let's find this first. So Rx, 394 multiplied by cosine 53, which is equal to negative 237 is equal to 0. Then which means Rx is equal to 237 Newton. We found Rx. It is positive, which means X component of this R must be in positive X direction. I am going to draw it. X component is in positive X direction, which is equal to 237 Newton. And now let's find the Y component. Ry, we don't know direction, we don't know in magnitude. This force is a negative Y direction, so it is negative 545. Don't write this. This is torque, not force. This force again, negative Y direction, 315. But that force has a component, positive Y, positive. F times sine 57, yani, which means 394 times sine of 53 is equal to 0. Now let's find this. Ry and negative 545, negative 545, negative 315, positive 394 times sine of 53, which is equal to negative 545 is equal to 0, which means Ry is positive 545 Newton. So Ry also must be on positive Y direction, in positive direction. Ry is equal to 545. And R must be vector addition because they are perpendicular. According to Pythagorean, we can calculate what R is. R is equal to square root of Rx squared plus Ry squared. So square root of Rx is 237 squared plus Ry is 545 squared. So let's finish this. 237 squared plus 545 squared, which is equal to this. Then square root of this number is answer. So R is equal to 594 Newton. R is equal to 594 Newton. So then here there must be a force acting in that direction, according to this, which is equal to 594 Newton. And we solved this problem, long problem.